Alright, so what we had seen was that we need an orthonormal basis, of a finite dimensional vector space. Fine, we need this. Fine, orthonormal basis. What we have know that V of finite dimensional implies it has a basis and it can be obtained from any non-zero vector. All right. So, we would like to do the same thing again here. All right. So, first let us try to understand what is called the Gram-Schmidt orthogonalization process and then get this. So, what is called Gram-Schmidt process. All right, it is called orthogonalization process that I am going to make it orthogonal. So, let me add the statement here. So, let S is equal to U1, U2, Un be any linearly independent set, then Gram-Schmidt's process gives a collection of vectors, gives a set W1, W2, Wn such that 1 length of Wi is 1 less than equal to I less than equal to n, 2 Wi and Wj their inner product is 0 for I not equal to j, and third, which is very important, very important, is that linear span of U1 to Ui is same as linear span of W1 till Wi for 1 less than equal to I less than equal to n. All right. So, what we are saying is that I am starting with any linearly independent set, I am able to get an orthonormal set. All right. This is an orthonormal set. How do I get orthonormal set? So, let look at this. W1, Wn has the property that length of Wi is 1, inner product between Wi and Wj is 0, and therefore, I get an orthonormal set. What is extra that I am having in this process is that the linear span is maintained. So, what you are saying is that linear span of U1 is nothing but linear span of W1, linear span of U1, U2 is equal to linear span of W1, W2 and so on. At each stage the linear span is maintained. All right. And the idea of the proof is just using projections. So, let us try to prove this construction. All right. So, let us get into this. All right. So, proof. How do I, what is this algorithm about? All right. So, define W1 as U1 upon length of U1. All right. So, the first is, so here I am giving the first element as U1, second as element as U2 and Un, and therefore, I am building W1 as U1 upon this. So, you can see that length of W1 is nothing but length of the whole thing U1 upon length of U1, which is nothing but 1 upon length of U1 into length of U1, which is 1. All right. So, this is basically the unit vector in the direction of U1. All right. So, once we have got that this U1 vector, so recall for us that what we had done was I had this vector V, I had U with me, there was this projection vector Q, P, O, then the projection OQ, this vector was nothing but, it was U inner product with V upon length of V into V upon length of V. All right. So, here for us it will be u comma w1 and w1 because w1 is a unit vector for us, all right. So, now I am going to look at this part. So, what we are going to look at, define V2. I have got W1, now I am defining V2, that is very important. V2 is define V2 as U2 minus U2 comma W1 W1. This is what we are defining, fine. So, what we are doing is look at U2, from U2 remove the composition, the component, the projection. So, this is the projection of U2 on W1, we are removing that part. Since we are removing this part, we are left out with this vector which is perpendicular, all right. So, you can see here, or you can use the previous theorem where we had shown that if I keep removing the components, so recall this theorem, which is a very important theorem that I have been saying it again and again, that if U1 to Un is an orthonormal set, then for any V belonging to V, the vectors V minus W and W are orthogonal, where W was looking at, all right, V comma Ui Ui. This is what I had proved in one of the previous classes, that things are perpendicular, fine. So, this I am trying to recall for you, very important, that if I keep removing any component, the whatever is left out is again perpendicular. So, this part tells me that V2 is perpendicular to W1, all right, because look at here, it says that this is perpendicular to this. So, whatever I am obtaining, the linear span is perpendicular to that part. So, V2 is perpendicular to this, I already know, you can verify that also, but this theorem tells me that this implies that this is 0, fine, that V2 is perpendicular to W1. I do not know whether the length of V2 is 1 or not. Idea was to get W2. So, the idea of the theorem was I want to get W2 so that the length of W2 is 1, fine. Length of V2 may not be 1. So, I have to get W2 to get things. So, I define, so this implies this because of this theorem. So, define W2 is equal to V2 divided by length of V2. Once I have defined this, this implies that length of W2 is 1. So, what is W2? W2 is the unit vector in the direction of V2, which is this direction. In this particular case, this is this direction that I am looking at, fine, direction of V2, and inner product of W1 W2 is same as inner product of W1 with V2 upon norm of V2, which is same as 1 upon norm of V2 upon W1 V2, which is already 0, fine, because of this part, fine. So, we have already got W1 and W2. How do I get W3? So, W3 again I define W3 to be is equal to, so the idea is if I want to define W3, I have to get V3, get V3 also, get V3 and write W3 as V3 upon length of V3, fine. Since I am doing this, I am dividing, so dividing by length of V3, we need V3 to be non-zero, fine. So, let us try to prove this part also. So, define first. So, if I want to get W3, I have to get first V3 and I have to show that whatever V3 I get, that should be non-zero, all right. So, let me define V3 as V3 minus, sorry, U3 minus, from U3 remove the component corresponding to W1, all right, and remove the component corresponding to W2. All right. So, what I have done basically here is I have got the set S prime as another set S prime, which is W1, W2. This is an orthonormal set. S prime W1, W2 is an orthonormal set. I am defining W as, fine, I is equal to 1 to 2, U3 comma Wi, Wi. So, what we know is that W and U3 minus W are perpendicular, are orthogonal. Orthogonal, fine. Also, so what we, from this part I get that, so this implies that V3 with W1 is 0, V3 with W2 is 0. Question is V3 non-zero? All right. So, if V3 is 0, that will imply that, so, or which is same thing as saying that V3 is same as this is 0, because we wanted to look at, we are dividing by norm of V3, not by V3 as such. Since we are dividing by norm of V3 should not be 0, and if norm of V3 is not 0 means V3 should not be 0, because this is the condition that I have, that V3 is 0 if and only if the norm or the length of the vector is 0. All right. So, I will assume that, so suppose, so let if possible V3 be 0. This implies that U3 is equal to U3 W1 plus U3 W2, and this implies that U3 belongs to linear span of W1 and W2. Fine. So, if you remember your results about linear independence and dependence, it says that as soon as U3 is in the linear span, implies that the set U1, U2, U3 is linearly dependent. All right. So, recall. So, again recall this theorem. Recall. Let U1 to Ui be linearly independent and V belong to V, then U1 to Ui comma V is linearly independent if and only if V does not belong to Ls of S, or which we say that V belongs to V minus Ls of U1 to Ui. So, not S here. So, U1 to Ui. This is what our theorem was in linear independence dependence. This is what we are using at each stage. So, let us go back. The statement here is that this is a linearly independent set. Our set S is linearly independent. So, at no stage, so linear independence implies that Ui does not belong to linear span of U1, U2 till Ui minus 1 for I greater than equal to 2. All right. Fine. So, this is what is important, that there are some theorems which we may not have thought that is so important, but they are playing a role, that you are taking that Ui belongs to the linear span will imply that this becomes a linearly dependent set. Recall also that the first time it happens, all right, I have a problem, fine, because if I am saying that this set is linearly dependent, it means that there exists a case such that UK is linear combination of the previous ones, that also we have proved. So, what we are having here is that S is a linearly independent set, and therefore, Ui is not the linear combination of the previous ones, and therefore, at each stage everything is going smoothly for us. All right, fine. So, now let us go back again, so that you have clarity with you. So, what we have done at this stage is, I have got W1 which was U1 upon length of U1, So, this implies that linear span of u1 is same as linear span of w1. Then we define w2 as v2 divided by length of v2, and what was v2? v2 was equal to u2 minus u2 w1 w1, all right. This is how we are defined. So, can I say from here that this implies that linear span of u1 u2 is same as linear span of w1 w2. Can I say this? So, understand here, if I want to look at linear span of u1 u2, then w1 is already a linear span of u1. So, this is in u1, I am looking at u2. So, this part implies that v2 belongs to linear span of u1 u2, and w2 is nothing but v2 upon this. So, this implies that w2 also belongs to, so w2 also belongs to this part, fine. So, both this belongs to, therefore, this is a subset of this. So, we have shown that Ls of w1 w2 is a subset of Ls of u1 u2, fine. Now, the other way around, since we have already shown that v2 is non-zero, so I can write u2. So, from here I can write u2 as v2 minus u2 w1 w1. This is just a scalar quantity. So, I am writing u2 belongs to linear span of w1 and v2, but v2 and w2 is the same vector, just the unit vector difference. So, this is same as linear span of w1 w2. So, we have shown that this is also a subset, and therefore, this is satisfied, fine. So, what we have done here is we have shown that I am going from u1 to w1, linear span of u1 is same as linear span of w1, u2 gives rise to v2, which gives rise to w2. I get Ls of u1 u2 is equal to Ls of w1 w2. At the next stage I have u3, I go to v3, this is not 0, similarly this was not 0 because of linear span of, so v3 does not belong to linear span of u1 and u2. I got v3, from v3 I get to w3, and again Ls of u1 u2 u3 will be equal to Ls of w1 w2 w3. Is that okay? So, this way you can build up the whole thing. At any stage, if I look at ui, so ui will give rise to vi. Now, why is vi not 0? Vi is not 0 as ui does not belong to the linear span of u1 u2 ui minus 1, all right. So, this is not 0, so I can go from here to wi, and wi, what is wi? Unit vector in the direction of vi, all right. So, in the process, that the way we are building up ideas, this will imply that Ls of u1 to ui will also be equal to Ls of w1 to wi, all right, fine. So, let me end it here. We will look at applications of this in the next class. Thank you.